Hello and welcome to our project about time series forecasting for power consumption prediction using recurrent neural network. Overview: I'm going to discuss problem and solution, business value, methodology, result and discussion, and conclusion. Business values. Resource allocation can be a business value of power consumption time series because it helps businesses optimize their resource allocation by identifying the most energy-intensive operations and areas of their operations. Businesses can identify areas where they are consuming more energy than necessary and make adjustments to reduce energy waste. Finally, it can help businesses plan their infrastructure capacity by analyzing historical data. Businesses can forecast future demand and plan accordingly, ensuring they have the necessary infrastructure in place to meet demand. The problem is how to accurately predict power consumption, which is crucial for effective load management and energy efficiency within smart grids. The traditional statistical models like ARIMA has some limitations because it assumes that the time series data is stationary and it requires the data to be evenly spaced in time, which is not the case in power consumption time series. The proposed solution is to use recurrent neural network with long short-term memory for predicting power consumption based on historical data. Our methodology started with data processing, model structure, model implementation, model training, and evaluating. The data is pre-processed by decomposing the power consumption data into its components using seasonal decomposition. The data set is organized into input-output pairs, which are sequences of data points with corresponding target values. The architecture of a model consists of the following layers: input layer, which receives the input features, which are time steps of power consumption data. Long short-term memory layer that contains a specified number of cells, each responsible for learning and maintaining the temporal dependencies in the data. Dense layer. This layer is responsible for producing a prediction based on the output of LSTM layer. And the output layer that provides the final power consumption prediction. Two baseline prediction methods are implemented: rolling mean and previous value. The model is compiled using the Adam optimizer, which is responsible for updating the weights. The loss function, which measures the difference between the predicted and actual values, and the R-squared metric, which is used to evaluate the model's performance. Training occurs from 2006 to 2016, which takes 3985 days, while validation takes place in 2017, which takes 365 days. The developed model demonstrates a strong performance in predicting the target variables as evidenced by the obtained R-squared values as shown. These values suggest that the model is able to explain approximately 86% of the variance in the data, indicating its effectiveness in capturing the underlying patterns and relationships. In conclusion, the developed model demonstrates a high level of performance in predicting the target variable as evidenced by the R-squared values for training, validation, and all data. The model's ability to generalize well to unseen data and maintain a strong performance across different datasets indicates its potential for practical application and future use. Thank you for listening.